Hola, chaps. Let's learn.
Hola, chaps. Mr. Turek here. This is for chemistry. Whoops, this is for physics students. In our study of static electricity, an activity that we would be doing here at the beginning of this unit is called the tape lab, where you would take a roll of magic tape or transparent tape or scotch tape and carry out a series of experiments with it. But to understand the results of what you see, I need to explain to you and give you some background information about tape. So here's my excellent drawing of roll of tape. And when you first pull the tape off the spool, the sticky side is presumed to be the side that gains electrons. So anytime that you have two different surfaces in contact with each other and you rip the two materials apart, at that moment, electrons have a choice to make. Do I stick with material A, or do I stick with or go to material B? And their answer is based on which of the two materials happens to have the lowest available energy state to accommodate that electron. You might remember that electrons prefer to be in the ground state of an atom, and if we give energy to that atom, like through a photon, then the electron can rise up to a higher energy state, but it generally doesn't like to be up there at that higher state. It would rather drop back down to a lower energy level. So if I have two different materials and the electron has the opportunity to choose which material to hang out with, it's going to choose to hang out with the material that has the lowest available energy state. And once that electron goes to that material, the material that it leaves, now that it's lost electrons, becomes positively charged, while the material that the electron drops down into has gained electrons and now becomes negatively charged. That is the basic concept that you have to keep in mind throughout this activity. There. I suppose you want me to go over that again, right? Or else you're going to hit replay. All right. So you take a spool of tape, assuming that you have these materials at home. And when you first pull the tape off the spool, we presume that the sticky side has electrons. That's just a definition that we're going to go with throughout this unit. Now, other stuff that you should know about electricity already. And if you don't, here's this handy dandy review. When you have like electric charges, two charges of the same sign, like charges repel. So if I had some positive charge and another positive charge, the outcome is that those charges would repel each other. What if I had two negative charges? Those are like charges. They like charges don't like each other. So they repel each other. Two positives repel two positives, negatives repel negatives. Great. Opposites attract. There's a Paula Abdul song that you could look up from the 1980s, Opposites Attract. And that theme of the song is also very true in the study of electricity. So anytime that we have opposite electric charges, positive here, negative there, they attract each other. Essentially, what happens often is that we have these neutral objects, and as we rip them apart, electrons go to the lowest available energy state, but now they have opposite charges, and aside from wanting to go to the lowest available energy state, now there's also this longing to get back to being a neutral object. So opposite charges are trying to get the electrons back to where they started from. And that is the tricks that we use to harness electricity to do all sorts of amazing things for us, like generate this YouTube video. So here's a fun fact. I suppose you don't know the answer to it, so I'll just pose this as a question first. What do you suppose would happen knowing that like charges repel, opposite charges attract? What do you suppose would happen if I had a positive charge and a neutral object? combined with each other. I mean, near each other. Would anything happen? So a neutral object is an object that has equal quantities of both positive and negative charges. Most objects in the universe right now are neutral. They have whatever number of protons in their nuclei and an equal number of electrons in their outermost shell for neutral atoms. Materials overall tend to be neutral. So would anything at all happen if I had a positive charge brought near a neutral object? Would anything at all happen if a negative charge were brought near a neutral object? I should make this a participation question, right? Sorry, I haven't learned how to do Ed puzzle. So the answer is neutral objects are actually attracted to charged objects. And here's my excellent drawing trying to get you to believe me. So here I've drawn a positively charged rod, let's say, and below it in the circle is a neutral object. It's neutral because it has an equal number of positive charges and negative charges. Now, per a previous episode, I told you that when we have a neutral object, we should use a checkerboard pattern to show the distribution of positive and negative charges. And so if I were to do a before drawing, before this positively charged rod came nearby, then I should draw a checkerboard pattern. But I've skipped that step. You hate my videos being too long anyways. And so now I've drawn a positively charged rod near what had been a neutral object and technically is still neutral because it has equal quantities of positive and negative charge. What makes it different, though, is that the protons are stuck and can't move, but the electrons are free to move. And so they redistribute themselves. The electron that had been over here on this side comes over closer to this positively charged rod. Opposites attract. Meanwhile, the protons are repelled. If they could move, they would move, but they cannot move. Don't forget that if I ever give you a quiz or test. The protons are stuck and can't move. These protons are stuck and can't move, but the electrons, being free to move, choose to move towards the opposite charge. And so they tend to pile up on the nearest side of this object, leaving behind protons on the far side of the object where those electrons had migrated from. Well, you would think that since opposites attract, that would be an attractive force, but like charges repel, that's a repelling force, and they should cancel and nothing should happen. But wait, there's one more little physics fact that I should share with you. It's called Coulomb's law, and it's an equation that you guys are going to have to learn sooner or later. Monsieur Coulomb, and I don't speak French, worked out that very similar to the law of universal gravitation, there exists Boltzmann's constant K times the charge on object 1 times the charge on object 2 divided by the square of the distance between those two objects. And that's what makes this neutral object not just sit there. Because while there is an equal quantity of positive and negative charge involved here on the two sides of this neutral object, and by the way, I'm going to start calling it polarized. It has induced polarization on it. What's going on is that the attractive force is ever slightly closer than the repulsive force and charges. And being ever so slightly closer, being in the denominator squared, closer, smaller number squared, means the force is stronger. So they're not an equal amount of force, even though they're an equal amount of charge. The near force, the attractive force, is slightly stronger than the repulsive force. And as a result, a neutral object becomes attracted to a charged object. But you ask, what if it were negatively charged? The answer is Doesn't matter. If this were a negatively charged rod instead of a positively charged rod, the electrons would move away from it and the protons would be left behind, in this situation, geometrically closer to the negatively charged rod. Once again, Coulomb's law says the closer two charges are to each other, the stronger the force is between them. And the attractive force, the force of attraction, how do I put this? The attractive charges will always be nearer to each other than the distribution of repulsive charges. So the attractive force will always win over the repulsive force. All right, so summarizing the key idea that you need in order to successfully do this upcoming activity, assuming that you can come up with tape. When two objects are ripped apart, the electrons go to the lowest available energy level, whichever one is lower. As a result, by gaining electrons, they become negatively charged. And what has lost electrons at the higher energy level becomes positively charged. Now, if you attended the Google Meet yesterday, then you saw me using my three fingers. And so the way that works is in concert with this handout that I need to distribute to you. Tape Lab, page 1. If you had something like a ruler, just anything where you could hang an object. Actually, I could use the side of this little object right here. If you were to take a piece of Scotch tape, magic tape off the spool, and this spool is just about empty, so I think I can only do this demonstration once. If I pull this tape off the spool, we presume that the sticky side of it, closest to you now, is negatively charged. And I'm going to set this, I should have prepared this ahead of time, right? I'm going to set this where it's just dangling there on the edge of your field of view, not easy to see. I'm going to take a second piece and pull it off the same spool, and the sticky side should be the negative side. What do negative charges do? They're repelling each other. I think you can just barely see that the first little piece is being pushed away as I bring the second piece near it. If I make an attempt to pull it, so I got sticky side this way, and if I go like this, maybe you can see there's an interaction taking place. Okay, yeah, not to my finger, but between tape and tape, they are repelling each other on their sticky sides. Okay, you can do this at home, right? What fun it is to do static electricity. Maybe I can do the top-down view. No, it's better if I do it in front of your webcam. So trust me, they're repelling each other. Can you not see that? See, repelling. It's not me moving the tape, it's the electrons repelling other electrons, trying to avoid getting close to each other. Of course, I suppose that means sticky to clear plastic should, well, no, it's not. So they're repelling each other and life is good. All right, so what you're going to do is take the first piece of tape off your roll and declare that to be the reference strip and keep it nearby. Eventually, over 20 minutes or so, maybe less, depends on the weather, the electrons will leak off through the air and it'll become neutral again. So you can't leave it there and use it all day long. You're going to take a fresh piece of tape off of the roll and use this as your test strip. So on your test strip, you're going to test a series of materials. I believe one of the materials that you are going to test is, no, I was going to say paper, but it's not listed. Okay, well, I guess I could do paper anyways. It does say plastic, and I happen to have a plastic ruler here. So grabbing this plastic ruler, taking the test strip, sticking it down on the plastic ruler. You can't see it. See, it's invisible tape. and making sure it's stuck to it. It only takes a moment. When you rip it apart, the electrons made a split-second decision. Gee, which one of these two substances had the lowest available energy state? They went to it. If the electrons went to the sticky side of the tape, then this tape is now negative all over again. But if the electrons went to the plastic ruler, then this tape is now positively charged because the electrons went over there. And when I bring it near the reference strip, if it is positively charged, what will they do? Pause, think. Yeah, they will attract each other. So here's my attempt at trying to demonstrate in real time. Ooh, they attracted each other. Oh, they're so happy together. So from this, I can conclude, okay, so my reference strip is eventually going to get mucked up. And good thing you have more tape than I do. This is the end of the roll. But with your pieces of tape, what you can do is then fill in the table. Let's see. In this example, which I could do for you, it says, when I put the test strip on plastic, which is number 3 here, which I have to rearrange, you can actually see number 3. Test strip on plastic, it says transparency, you don't have one, you can use a plastic ruler. What happens when you put the test strip near the reference strip? Did they attract or did they repel? They attracted. And I'm going to do shorthand because I'm just a teacher. You, of course, get to write it out. I'm going to put A for attract. I'd probably use R for repel. Next column. What was the charge on the test strip? Okay, so you have to work through your 3 fingers. The reference strip is always negative, and if the test strip attracts to the reference strip, then they must be opposite in charges. And if they're opposite in charges, and if the reference strip is negative, then the test strip must have been positive. So what was the charge on the test strip? Positive, which is what I'm writing down somewhere where you can't actually see it. Next, did the test material give electrons to the test strip or take electrons from the test strip? Well, the test strip lost electrons to the test material. Reference strip, always negative. Test strip, well, you test it, hence the name. Test material that the test strip was ripped from is going to be opposite in sign to whatever the test strip is. So if the reference strip, which is always negative, attracts the test strip like it did in this example, then the test strip must be positive. Opposites attract. The test strip is always opposite the test material. So if the test strip is positive, the test material is negative. And to answer this question, did the test material give electrons to the test strip or did it take electrons from the test strip? The answer is it took electrons from the test strip. So, did it give or take? We will say take as a single word answer. So, took, past tense, taking, current tense, English. Sorry, English teachers. So, filling in this worksheet, here's one row of it. Which material, the adhesive, which is the test strip, or the test material, offered the lowest available energy orbitals, orbital orbitals? Well, the one that ended up with the electrons is the one that had the lowest one available. So test material or test strip, which one should I put down? I should put down test material. And if you want to be really specific, like some of my students, you would say the plastic ruler. But okay. So here's an example filling in one of these items on this worksheet that I'm going to share with you. This video, YouTube video, goes along explaining it to you. And as if listening to the sound of my voice didn't make it perfectly clear, why, you could create this handy dandy reference sheet, which is also a handout I can pass out to you. Imagine that this ruler here is just that, anything that holds your reference strip. The reference strip is always Ms. Revlar would want me to fill this one in using Edpuzzle, I'm sure. The reference strip is always negative, and it's got all these minus signs on it, meaning it's negatively charged. If the test strip is observed to attract the reference strip, then the test strip must have a bunch of plus signs on it, and the test strip is positive. That's supposed to be an O. Positive. Ta-da! Simple. Just physics, child. So, how does the test strip become positive? Well, okay. True, when we first pull the tape off the spool, you've been taught that the sticky side is negatively charged. But when I stuck the sticky tape down on the test material, we're going to claim that we're resetting the situation and that now the test material and the test strip are both neutral. So ideally, this should be an alternating checkerboard pattern across the two substances. Instead of plus lining up to plus and negative to negative, it should have been plus lining up to negative and negative lining up to plus as we go across. Charge, you can put 0 and 0. Actually, neutral is a better response. Oh well. Let's put N, no, because some students, if they put N, they'll think that means negative. So we'll have to go with 0. There we go. After you pull the tape off, what is the new situation? The test material is going to be opposite in sign to the test strip. The test strip was positively charged. So here is our test strip positively charged, and therefore the test material is negatively charged. This is positive, that is negative. What about the rest of the checkerboard pattern, you ask? Look, if you start drawing some of the nearly countless trillions upon trillions of actual plus and minus charges in any substance, it's going to be hard to grade. So let's simplify it this time, right? Hola, chaps. Let's simplify it and just show me the net overall charge. So overall, even though the test strip has trillions of electrons in it and trillions of protons in it, it's lost 8 electrons. So overall, it's got an imbalance and a net positive charge. And I was just being, figurative when I said 8 electrons. It's really trillions of electrons there too. And trillions upon trillions upon trillions. You have to deal with moles, 10 to the 24th and higher numbers of these things. So don't draw them all. Don't even draw 2,000 of them. Don't even draw 800 of them. We're just trimming this down, right? Okay, so that is half this reference sheet. This other half is where you put your name and you are, oh, wow, you could be Aaron, I suppose, unless you're someone else. But in this situation, suppose, just suppose, I have my reference strip here and it's negative, just like it's drawn here. Yes, I can do that. And this time I bring my test strip near it. There's my hand, the fickle finger of fate. And this says, oh, this time it's repelling. They're pushing each other away. Well, if you can think back 2 minutes, then you remember that like charges repel. And therefore, the test strip is negative, and therefore, you should sketch some minus signs on that reference strip. How does a test strip become negatively charged, do you ask? Well, same flaw with the other side of this handout. This should be an alternating checkerboard pattern with equal numbers of positive and negative charges. So 0 and 0 because we don't want you to confuse neutral with negative. When you pull the tape off, the test strip needs to end up the way you drew it here, meaning the test strip has to end up being negatively charged. So this is negatively charged. The test material, which lost those electrons, has these protons left behind, and therefore it is positively charged, and you have a handy dandy reference sheet to refer to as you complete filling in, here, I'll show you this way, filling in lots of test strips. So the left column on this is the before condition. And what should it always be? It should always be not like the first example, but an alternating checkerboard of plus, minus, plus, minus, minus, plus, minus, plus, and not 10,000 of them, please. The after situation. So here's the test strip above the test material after they've been ripped apart. Test strip above the test material after they've been ripped apart. Oh, you're going to have to substitute for the lab table because I'm not going to let you go into my classroom, am I? So substitute for the lab table, dining room table. Dining room table. If you have aluminum foil, do it. Instead of plastic transparencies like what we used to use in the last century for teaching, you may use a plastic item, ruler. You could even say, oh, I used Mr. Turek's ruler. You may substitute a tree if you need to, but you could use a wood block. Of course, you have a mirror. Nylon? No. Cotton fabric? Yes. The plastic side of the tape. So, what happens when you put tape over tape? If you have it, wax paper is something you would tend to find in the kitchen. Saran wrap is a company name, brand name, but it's also an item you would tend to find in the kitchen. All right. So there you have it. Have fun. Think of this as an assigned activity with these worksheets. Welcome to static electricity. Ciao.